So today we're going to be talking about freeze. So I'm Yeshwanth Kumar. So how many of you here are using freeze in their day-to-day code? Free monads? No. Okay, so quickly about me. So I was previously co-building this DevOps-based automation platform. So when it works on top of Docker, where it helps developers, do single-click deployment, things like that with CI/CD baked in, right? And I moved to London. It's been 6 months. It's pretty hot this month. And currently I'm working for CHS. We're a telecom company. We are building a cloud-based contact center platform, right? And finally I'm writing Scala full-time. It's fun, right? So yeah. So what is free monad? This is the definition you get when you Google it. Free monad is a construction which which allows you to build a monad from any functor. Okay, so let's move away from category theory for a bit, right? The only thing you need to note here is, like other monads, it is a pure way to represent and manipulate computation. I think that's where we're going to mainly focus on. Okay, so I mean, when I first started with free, I was doing a lot of object-oriented. I was doing like imperative self-coding, and I moved to Scala, and I was trying to do writing code in pure functional way. It was like what the heck is this? I mean, this is So let's just go deep into why do we even need free monads, right? Like I said, the talk is primarily going to be focused more on how we're going to be using free monads and how you could actually right now go back and start using it, right? So one of the major things I'm sure you all know is isolation of side effects. So and every time we build something in a functional way, there are two things. One is we have side effects. Another one is we have pure functions, right? Ideally we have pure functions, we have side effects. So your software, which is going to be talking to other microservices, your API servers, your DB, your cache, right? So free monads help you isolate your side effects, right, from your pure functions. So that helps you keep everything pure, right? And another thing is that it helps you increase composability. So ideally, let's say you have a typical you're communicating to a typical HTTP API server. You have get, put, post, whatever, right? So those are all operations that you're performing in your software. Okay, so what you would do is those operations are defined in a pure way. Okay, and you define a business logic using those operations, and and you have your interpreters. That is the place where you actually call and make those HTTP requests. They both are separate. We're going to be looking at that in a minute. But the idea is that you would have a very lightweight sort of a domain-specific language on your own, which you can reuse, compose, use them push them as a library and use them again and again, right? So let's move forward into writing free programs, right? So it's quite easy. I mean, if to start with, there are 5 major parts. One is, like I said, you have certain operations, like in a typical, HTTP or get, put, or you have your, put for if you're doing a key value store, you have put, get, or whatever it is, right? So you have certain operations that you would do in your software, and you define them as case classes. Okay, so you define your ADTs, okay, and you have your interpreters. So interpreters is where you define your implementation of what you want to do with those specific case classes. Okay, we'll look at it with sample code. Smart constructors. Okay, so smart constructors are used to lift a specific algebra or a bunch of operations that you've defined into a freeze context. We'll look at it in a minute properly, but so just understand that in order for you to flat map something, typically in a for comprehension where you write your business logic, you want to lift your algebra into the freeze context, right, for you to be able to do anything with it. So that's where the smart constructors, that's what smart constructors do. And program is basically, you've defined all your operations. Obviously, you want to, use them to build and write your business logic, right? You want to do a get, and then you want to store something, you want to do some pure logic, and then you want to. So basically, they represent your business logic, and you compose them using your algebras, right? And so if you notice, until here, whatever we've defined, they're pure. Your case classes, they're pure, and smart constructors are just helpers, and the program is still pure. And interpretation, this is where you take your program, which is basically a bunch of free, and you give your interpreter, and you actually perform the side effect, right? Okay. So let's just quickly look at the code. So the first step is, like I said, defining algebra. So it's going to be, over here we're doing a simple log example where we're performing two operations here, info and error. Typically, you're going to be having. So if you notice there, its return type is unit. It extends log. Return type is unit. That means it's performing some side effect. Okay. So we got info and error. So this you define, and yeah. So there you go. These are the helper functions, two helper methods to lift to freeze context. That is basically what we are doing here is info returns a free of that specific operation that you're performing. It lifts into the freeze context. So if you can see lift f of log unit f comma a, right, your operation and your return type, and then that's the case class that we're passing in. Okay. So now your interpreters. Okay. So if you notice here, this is where we actually perform our side effect. Okay. We'll all put this together, then it'll make sense. Okay. But so as you can see here, log interpreter, it extends. So this is function k right there, which is log is basically your operation, that your algebra that you specified, to another monad or a type with a hole. You say it. So that's a natural transformation, that little symbol right there. Okay, we'll look at what function k is, but ideally you would need this, and this is where you would be writing your logic as to what you want to do with that specific operation. So make sense? So in this case, we're saying we have an apply method which takes error and info. So whenever, so let's look at the program. Whenever this is the program, your business logic. So over there, when you use info and error, of course it's going to be a lot more depending on your algebras. So when you use info and error, we know that it's lifted info and error. It's lifted to freeze context. So obviously you'll be able to flat map them. And okay, so when you actually interpret your program, this is the final step that you do. When you interpret the program, you pass in the log interpreter. So program dot fold map. So basically free would have a fold map method, right? You would basically fold map and then pass in the log interpreter. Okay, and that's where the actual interpretation happens. It fold maps and goes into your computational tree. That is what you've defined there, and then it sort of applies. This apply method gets called. So if you use error, it's going to go print it. Likewise. Okay. So let's look at the code. Let's see if I. We'll open IntelliJ. Okay, I think this is simple. Okay, this is not exactly log, but it's kind of the same thing, right? You can see we have a seal trait. Can you all see? Yeah, so that's no. Yeah. Oops. Yeah. So this is, as you can see, I've given a type alias. This is basically free. Okay, that's a pretty good example, but as you can see, this is my algebra. So it's just left array, right array. It's just trying to. And you have your interpreters here. All they do is just this is print. That's all. I mean, as you can see, this is your two algebras, left and right, and then you're having your fire interpreter, which kind of fires. I don't know. And then this is your lifting step, where you actually f of a, that is basically this guy here, your algebra. Just consider this as log. Okay, I don't know why I have fire there. My bad. And then left and right. So this is basically what they lift to the freeze context, and as you can see the program right here, which I'm using left and right. They are basically my algebra. Okay, and I'm actually fold mapping them and giving that interpreter here. Okay, this is very simple. I'm just gonna quickly run them. It should ideally print for me. It's running. Let's see, I'll just show you in here, it's easier. Yeah, okay, it's the same code, I think. Yeah. So as you can see, it's the same thing. I'm just fold mapping my program and passing my interpreter. So if you run it, as you can see, it's actually printing left, fire in the hole, right. Okay, so the thing is, now you can ask me, I'm just using one set of algebras, right? That's not going to be the case. When you're writing a business logic, that is this program right here, when you're writing it, you're obviously going to have a lot of things, right? So let's say, like I said, you might have an HTTP server, you might do a get first, and then you might want to, store that in your local DB. So another side effect that you want to perform, right? So your program's obviously business logic is going to be a lot of things together. So you would obviously want to combine multiple programs, multiple algebras or operations together, right? So that's where Coproducts comes into picture. So what you do is, so let's say we want to log something like we initially saw, and you want to store something. Okay, so in your store algebra you might have, like I said, put, get, update, delete, right? So this is how you would use the coproduct to actually combine your algebras together, right? And then use them in your program. Does that make sense? So basically what you would do here is, you have your log, you have your store and the return type, and my app basically represents your log and store. So you could, in your program, you could, pass in my app, or rather in your smart constructor, which we'll show you in a bit, pass in my, so you would be able to use all the algebras from these two, right? And you can interpret it, okay? You could also combine, let's assume now we're having a third algebra, right? Third set of algebras, third set of operations, let's say, some of the external microservices that you want to talk to. You could again use a coproduct of that, comma, my app, comma, of A. So basically you could compose all your operations or your algebras, together and then interpret them, okay? Fine, you can ask me, now I'm able to combine this, but let's say in my previous program, what if I just use put from store? The interpreter is not going to know if I pass in log interpreter, right? Because it doesn't know how to interpret that specific algebra. So that's where you use a combined interpreter. As you can see here, you obviously define your store interpreter and log interpreter and all the interpreters involved for this specific, for the specific algebra, and then you pass the combined interpreter into when you fold map them. So program.fold map of combined interpreter, the function k basically, and it would interpret for you. Just show you a quick example. So if you see, it's definitely not visible. Let me just use. So as you can see, we have log. Again, it just prints. That's all. And you have your store. Assume this does some side effect. It's return units. It assume it actually in your interpreter you actually written saying that it goes. You use the API. It communicates to that external service and puts and gets the data. But in this case, I'm just printing it again. Okay. And you can see those two interpreters defined in here. So these are your two algebras, log and store, put, get, info, error, perfect. And these are your two algebras, log interpreter, two interpreters, log interpreter and store interpreter. And I'm just printing them, right? Okay, so this is our smart constructor right here. So what we do here is this basically just lifts. We don't use lift F here. We use inject to basically inject our type into the freeze context. Think of it like that. Okay, so that's what we do here. So that's basically log h and store h. It's just helper methods, smart constructors, and you have implicit to actually create that instance. So you just need to define these two. Okay, so now you know that they are lifted to the freeze context. So basically when you're using them in your program, as you can see here, implicitly log h, store h, right? And you pass in your my app in there, which is a coproduct. You follow it? It's a coproduct of bunch of your algebras together, and you're using your program here. So I'm just doing info and put. So info is from the log algebra and put is from your other your store algebras, right? And I'm doing a combined interpreter here. As you can see, my app to ID. This is the function k, right? So my app to natural transformation ID, and I'm doing log interpreter or I could also, let's say if I have more interpreters coming in, I could do the same thing. I could use some other interpreter or combine interpreter. So what I'm saying is you can add more things, right? So over here I'm fold mapping program. This is our program right here. Dot fold map, and I'm giving the combine interpreter. So if I run this, I think it's already running. Okay, now this doesn't work. So let me just quickly run that in here and show you. It should. It's very slow. There you go. It printed boo and put something, right? So as you can see, so the thing is, if I remove, oh, there you go. So the thing is, if I remove this final program, right, it's not going to compile. It's not going to actually interpret. Right? This is where the actual interpretation happens, right? So this thing, this is loose. My bad. Yeah. Okay, so if you don't have this, so everything else is pure. Your case classes, your smart constructors, and your program, everything is pure, and this is where you do the actual interpretation, right? So now we can combine multiple algebras together and do it as well. Okay, so the idea is how we used free monads in our code. So we have a CQRS event sourcing sort of an architecture where we have a lot of actors. So we get commands, and actor does something, it performs a lot of side effects, and it emits events, and the events are persisted in the Cassandra store, and so, right? So this actor performs a lot of side effects. So what we do is all these business logic, let's say we get a command which is supposed to do 2 to 3 things, we have them as a pure function, like the program that you defined, that I showed you. We have them as a program, and this actor executes that program and interprets it inside the actor's context, right? So one benefit is that if you want to test it, you could pass in a test interpreter which doesn't actually talk to external service. In this case, it's log, but in case let's assume we have a store, you don't actually need a store, to actually put things in check. You can just return saying it was successful, right? So in that case, if you want to test this, you could use test interpreters and just test your pure functions only, right? You don't even need the whole actor system in place to actually test them, because testing with actors is a little hard, right? So this way you're able to test all your pure functions, all your business logic really well. So it kind of really helped us in that sense. And yeah, so Freestyle. So Freestyle is a library framework which really helps you, to cut down a lot of boilerplate. It becomes a breeze to write free monads, to start using them immediately. And you saw the lifting part, right? Everything it takes care, and it helps you compose things really well using modules. And it's the same concept, it's just different names, and it really helps you to sort of compose things together. And it's a macro based solution, so all your boilerplate is generated, right? The code is generated. So we'll just quickly look. We saw that we define algebras, we define modules, the interpreters, and our program, right? And the coproducts and combining interpreters, right? So we'll see how we would do the same thing in Freestyle. So you define algebras like this. You do have a free of trait store, and you define 2 methods. This basically generates case classes for you, right? So that's your algebra right there. And your interpreters is quite simple. You have an implicit val. You call your algebra store dot handler, and then I'm not using id here, I'm using the state monad, but ideally you define what you want to do with this interpreter, right, which is called handler. Ideally you want to say what you want to do with that specific operation or your algebra that you've defined, right? So that's your algebra, these are your interpreters. Okay, so coproducts, so basically they have this concept called modules, where you combine multiple algebras that you've defined together, and you call them as a module. And in your program, you're able to define a program, and you define a program, and you're able to interpret them. Okay, so it's quite simple, because it's very powerful, because you define this guy right here. You define your algebras. You're going to have multiple such algebras, like I said. It's very simple, and then of course, interpreter. So this can be called store, or this can be called log, or your, like I said, HTTP server. Which, and inside the method you actually say what you want to do. Okay, you define your interpreters, your handlers, and your coproducts. So coproducts, I mean modules in Freestyle's context, is that you use all these algebras together and you compose a module, and you use that module when you're executing your program. Okay, when you're running your program. The thing is, you can have such modules, you can compose modules from other modules and use them, right? So and they also, you don't have to really do the whole, you know, smart constructor, and you don't have to really do the or the coproducts. Everything is taken care. All you have to do is write a module trait, the application, and then say log and store, or whatever you want to use, right, inside that. And you just need to import your algebra, that's right there, and then this is how you interpret it. And you just need to provide your module, your interpreters, I mean it should be there, your interpreters and your algebras. The module represents that, and then program my application dot interpret. This is very similar to interpret. Basically does a fold map, like what I previously showed you with cats. This kind of does that. So they have a wide range of, they support a lot of integrations like Akka HTTP with Finch, so it makes it super easy to work with. And FX, they also support FX, which state reader writer, like with added, so FX kind of adds capabilities over what you're trying to do, right? So yeah, to get started with free, there are few open source tools, because I was trying to look at open source stuff to learn from, right? So Scala exercises, I think they use Freestyle. So if you want to really try to understand, you can pick it up. And Doobie is again written in a lot of cats in free, so the code is pretty good. And Slate is also a project which uses free, right? And that's something you can look into and try to understand. So yeah, that's it.